Hey, what's up, guys? So I know this sounds like a ridiculous project, but everything you see in this video can be used for other applications. And we're even going to get into low power design because the project I'm showing you here is battery powered, and I need that battery to last for years. So basically what we're doing here is creating a non-invasive system to monitor my washer and dryer. And when I say non-invasive, I just mean that we're not going to hack into the washer and dryer. Just monitor it from the outside. And we'll get into that in a second here. But basically, I have a really cheap washer and dryer that they don't have buzzers or alarms or anything when the cycles are complete. So the inspiration for this project, of course, came from me forgetting my clothes in the washer. I was doing dress clothes to make matters worse, and I had a huge wrinkled mess on my hands, and I figured, man, it'd be cool to throw some sensors at this, some cool circuitry and Arduino, and send off a buzzer when the washer and dryer are complete. So let's go ahead and take a look. Okay, so we're in the laundry room, and you can see we've got the washer and dryer, and again, I wanted to keep everything here non-invasive, meaning I didn't want to hack into the appliances, just monitor everything from the outside. And the washer was very easy to monitor because we've got lights, you can see them up there, and one light turns on when the cycle is complete. So that was actually pretty easy to monitor. I just needed to hook up a CDS photoresistor or light dependent resistor. We'll talk about that in a second. And it's just black taped right up against the sensor over there to monitor it. Right over here is the actual control board. I've got a little 9-volt battery hanging off of it, and that's what's monitoring both the washer and dryer. So the dryer, on the other hand, was a little bit more challenging because I don't have any lights. You might remember from a few videos back that the knob assembly there does have a pair of contacts for an alarm. But again, I thought it'd be cool to monitor this from the outside. So I thought about how was I going to do this, and maybe, we could put a magnet on the drum, and then as it's spinning around, we can somehow detect that magnet. Or maybe we measure the current, the AC mains current feeding the dryer, and then as soon as that turns off, we'll know that the dryer's off. So anyway, that was one option. But what I ended up with was actually monitoring the vibration of the dryer. And you can actually get vibration sensors, but I thought, well, I don't have one of those. So I went and checked out my junk pile, and I found a piezo element right out of I'm trying to let's see if I can get in there. So you can see down there I have a piezo mounted to the dryer with some magnets, and I'll actually pull that up real quick here. So I'm going to detach that. Okay, so I have just a standard piezo disc there, and it's actually held onto the dryer with some magnets, just like that. And that actually is monitoring the vibration of the dryer. So that's how I know when the dryer is on. And that's what arms the system. So it's armed when it sees that vibration, and then it will set off the alarm when it no longer sees vibration. And of course, it's a piezo, so we're not talking about a huge signal there. It's a very tiny signal that we then amplify up through a circuit and then peak detect on. So we'll get into that too when I show you the schematic. But let me give you a quick demo here. Okay, so I've got the piezo back on the side of the dryer, and the dryer is running right now. I would show you how the washer works, but I'd actually have to run it through a full cycle. The dryer is easy because I can just turn it on and off. So right now the board is monitoring that piezo, and it checks the piezo once every 8 seconds. And in order for it to arm the system, it needs to see vibration on that piezo disc at least 10 times in a row. Okay? Then when the dryer turns off, it needs to no longer see that vibration 10 times in a row. Okay? So when it sees that, it'll know the dryer actually turned off, and then it'll throw the buzzer flag. So let's let that just go. Okay, so now I just turned off the dryer, and we're going to wait now for the board to take 10 consecutive measurements from the piezo to make sure that the dryer is off. Okay, and there you have it. Now the buzzer is alarming because the dryer has determined that the dryer was on. Now it is off. And then, of course, to reset it, we have a button right there. And once you press the button, it resets. And now it'll wait for the dryer to turn back on to rearm itself. And then again, to throw the alarm again, it would have to wait for it to time out without any vibration. Now, the same is true for the washer over there. So with the washer, the LED turns on. Right now, the washer is armed because the LED is off. That cycle complete lamp is off. So it's armed, waiting for the LED to turn on. And when it sees that turn on for 10 consecutive tests in a row, it will throw that alarm. And then when you press the button, it disarms the system and waits for the lamp to turn off. So that's how it actually works. Now let's get into the circuitry for monitoring these appliances. Okay, now we can get to the good stuff. Here is the control board that is monitoring the piezo disc and the light sensor. And by the way, all of these boards here are boards that I designed, that I use in my own projects, and they are available. So check the description below for links to where you can get these boards. Sorry about the commercial here, but this bottom board is what I call the platform board, and it's basically just a very simple board with slots for various little mini boards that I designed. So this is an LDO board here that has a really nice low quiescent current draw voltage regulator on it. So it's great for battery powered applications. The regulator only pulls like 2 microamps, and I soldered on a little 9-volt battery clip to it. And as long as it's sleeping, you know, I'm not too worried about the efficiency, so I didn't really need a step-down buck for this. But anyway, yeah, that's the LDO board, and again, it can go into any one of these slots. Right in the middle is the 328 board, which is kind of like an Arduino Pro Mini, and it is programmable right from the Arduino IDE. And of course, I have a little USB to serial converter to program it from, just like that. The board is also compatible with the BLE board, so in fact, I could add Bluetooth Low Energy to the system as well, so I can monitor it from my phone or push a notification when the laundry is done. That would be kind of cool. But again, you know, the board supports 3 mini boards, and right now I'm only using 2 of the slots. I thought about even powering the whole thing from a coin cell, and I also have a little coin cell board here that plugs into it. And down below here we have what I call the proto area, or the playground area, and this is just a little proto board area where you can put your own customized circuits. And that's where I have the op amp and the peak detect circuit, the buzzer, the button, all of that soldered onto. And right here we have terminal blocks, so you can connect up external sensors, and that's how I have the piezo terminated into the board, so as well as the light sensor. I couldn't bring that over though because it's taped pretty good up to the washer. So yeah, that's pretty much it with the board, and I'll bring this back, but let's jump into the schematic here, and I'll show you how this whole thing works. Okay, so here's a little rough schematic of what's going on here. You've got the piezo section and the light detector, or the light sensor section down here. So let's just start with the piezo, and this was actually kind of tricky, but once I got it working, it was really, really cool, and I'm actually going to continue to work on this and tweak this design a little bit. But I got it so good that when I had the board like sitting on my desk with the piezo just sitting here, I was able to like tap on the other side of the bench and pick it up. So, you know, I was thinking, boy, you could do a lot with this, like monitor like equipment or whatever if somebody's trying to steal your motorcycle or whatever, you know. So you could do a lot with that. It can be very, very sensitive. So here is the circuit that handles the piezo. So right over here is the piezo disc, and you can see that the center pad there, I've got wired that's coming into the board. The other outer ring there is terminated right to ground. It comes into the board. I have it clamped, so I've got 2 diodes to clamp it so that my input doesn't go above 3.3 volts or below 0 volts, just to keep it within range. And right here is a very important part of the circuit, because the piezo is very capacitive in nature, and if I just let it kind of hang out there, it would build up a charge and just hold that charge. It wouldn't go anywhere. So you could either put a resistor across the piezo to bleed it off, or you can put in an active system that dumps the charge off of the piezo before you take a measurement. So that's what I did. So right here, we've got an NPN transistor. This is actually, forgot to put it on there. It's a 2N3904 standard NPN transistor. And it's connected through a 1K ohm resistor at its base to digital pin 6. So when digital pin 6 goes high, it dumps the charge off of the piezo through a 100 ohm resistor to ground. And then at that time, I'm ready. I've got that super high impedance. There's no resistor across the piezo now, so it can take in, and it's very sensitive, and any little movement on that piezo will create a voltage, which comes in and feeds this op-amp circuit, which might look familiar. I'm using the same op-amp that I talked about in my last video, the MCP6242, and I'll put a link to this in the description below as well. I've just got tubes of these things laying around. You get 2 op-amps actually in one dip package, so you probably can't see that, but it's a tiny little dip package, which is an 8-pin dip. I'm not using one of them, so I just tied the output of that one back to the negative pin and then grounded the positive pin. So I'm not using that one. But I am using this guy here with a gain of 11. So I've just got a 10K and a 1K there and a non-inverting configuration there. And, you know, one of the things I wish I would have done here is put a pot in instead of this 10K so that I could adjust that gain. And I might go back and do that because I don't know. I feel like there could be a sweet spot because right now the gain is so high that, you know, it doesn't completely settle back down to 0. And I want it to be sensitive enough, but not too sensitive, you know, so it's trying to find that balance. But right now with the resistors, it is fine, but I would like to work on that a little bit. So that gains up the signal. And then right here is a peak detect circuit. So as you have like movement here and it's dancing around, it goes through this diode and charges up this capacitor here, and then it just holds it. It can't backfeed into the op-amp. So like if you pulse to this thing, yeah, I could write on this. So if you had a pulse right here like that from, you know, vibration, it would, on the capacitor over here, just hold that charge. And it would actually kind of droop down because I've got a 1 mega ohm resistor across that capacitor. And the reason for that is because I do eventually want it to discharge, right? So that's kind of what's going on there. And then that's read into an analog pin on the 328, the analog pin 0. And again, that was another variable in the system. Were the values here of the 10 microfarad capacitor and the 1 mega ohm resistor. I was trying to find a good balance there. So, but this works great, what I've got going on here. The other thing that I might play with are the values for these diodes. These are the only diodes I just had laying around, and these are just 1N 4007 rectifier diodes. I might change those out and use Schottky diodes there. Same thing with this diode here. So anyway, it works okay for now, but I'd like to see if I could actually improve on this a little bit. So that's kind of how that works for the piezo measurement. The light sensor circuit is just dead simple. This, again, you know, is a standard light sensor, CDS cell, sometimes referred to as an LDR, light-dependent resistor, or a photoresistor, and it just basically changes its resistance with respect to light. So I measured this one here. When it was dark, I got 12K ohms. When it was light, when I shined some green light on it, because that's the lamp over there in the washer, I measured around 400 ohms across it. So what I got going on here is on one terminal pin, I'm actually sending out digital pin 7 here. So it's hooked up to a digital pin off of the Arduino. That's going out, powering the CDS cell. And then that's just setting up a voltage divider here with a 10K ohm, because when it is dark, it's at 12K. So we've got like a pretty nice balanced voltage divider there. So like when it's dark, I should get a value on analog pin 1 of like 512, somewhere like right between 0 and 1023, something like that. And then when it goes light, this resistance here decreases down to about 400 ohms, so it's pulled up high, so it'll go up, close to 1023. And when we get into the code, you'll see how that works. But I have a threshold when it detects light. Now you might be wondering why I have D7 controlling that. Why not just connect that up to 3.3 volts? Well, like I said, this is a low power design. I want this whole thing to run off of a battery and last for years. And it only takes a measurement every 8 seconds. So I want to power this circuit up here on demand, only when I need it. And it's low current, so it's like no big deal to power that off of a digital pin. So when I'm about to take a measurement, I apply power to the system through digital pin 7. Same thing for the op amp up here. So I didn't really talk about that, but you see I've got a decoupling cap across the power pins for the op amp, and digital pin 7 is applying the power to the op amp as well. So that's like my power pin into the system. And again, you'll see that in the code. Okay, so that's pretty much it there. And then digital pin 3, which is an interrupt capable pin for the push button. And I've got the internal pull-ups enabled on that pin. So when you push that button, it pulls the signal low, falling edge, triggers the interrupt, and you're good to go. Then you've got the buzzer on digital pin 8. So that is the complete circuit there that I've got soldered in down there on the control board. And I've ran a few loads through the washer and dryer, and this works great. So I'm really impressed with it. I'm happy. So now let's jump over to the code, and I'll show you how that all works. Okay, so here's the code, and it's pretty straightforward. Again, a lot of variables in here to tune, to modify the system performance. But right up here at the top, I define all of the pins. So you get the button pin, the piezo reset pin. That's the charge dump transistor control pin. Here's the power pin, digital pin 7, buzzer pin, and then the 2 analog pins for the sensor inputs. And then here are the thresholds. So the piezo threshold, if I ever see a value greater than this value, I know that the dryer's on. I detect vibration. If the light is ever greater than 700, like we talked about, it's starting to clamp up to 3.3 volts, then I know that the light is on. Okay? And a couple variables for reading in the raw values, and then a whole bunch of Boolean variables here to detect the various states or flags of the system. And we'll talk about these kind of as we go. So I'm just going to skip down here. Got a little function in there for controlling when to go to sleep. And right into the setup, we just set up all of our directions there. Serial.begin there for debugging only. And then, of course, we've got an interrupt attached to interrupt 1 because it's digital pin 3. Digital pin 2 is interrupt 0. Digital pin 3 is interrupt 1. Calls this function button pressed when it sees that falling edge of that pin. Now, this stuff right here for the sleep mode is a direct copy from the video I made on Arduino sleep modes linked here. So go check that out. I'm not going to dive back into all that stuff again. But all of this is right from there. And I'll explain at least what kind of sleep mode we're getting into. Okay, so right in the loop, it immediately starts with a measurement. So it has to power up the op amp and voltage divider for the light sensor. It does that first. Then it resets the piezo by dumping all of the charge on it. So now it's fresh, and it can take in a new measurement. And then it goes to sleep here with a prescaler value of 0, which is a 16 millisecond deep sleep using the internal watchdog timer. Okay, so what's cool, right? What's happening right here is the Arduino goes to sleep. It's actually enabling the internal watchdog timer, and it goes to sleep and then wakes up at whatever value you put in for the prescaler. So let's jump down to that function. It's down at the bottom here. Go to sleep. So you can see here that it's going through all the steps from that video I made on sleep modes, and then just loading up that prescaler in for the register here, WDTCSR, And then I actually copied a chart out right here from the data sheet. So all zeros right here in equals asleep for 16 milliseconds. And that's an approximate thing. It's not very accurate, but for what we're doing here, it doesn't have to be. So it goes through all of that, kills the analog to digital converter, and then actually goes through the sequence to put it into sleep mode. And then it just wakes up when it wakes up right after this point here, kicks on the ADC, the analog to digital converter, back on, and then just carries on from wherever it was at. Now, the thing here is that not only does the watchdog timer wake it up, so that's 16 milliseconds after that elapsed, but also the push button, which is important. So if I'm sleeping for a long period of time, I also want the button to wake me up. And when the button is pressed, of course, it calls this function down here and throws this flag. Button was pressed is equal to true. Okay, so again, that's all copied from that other video, so check that out. But let's get back to where we were, and that's right up here. So we sleep for 16 milliseconds, wake back up, so we just let it just, discharge that piezo, make sure everything's ready for a fresh measurement, and then we drive that pin low, so now the piezo is wide open, ready to take a measurement. Go to sleep with a prescale of 2 now, which is a 64 millisecond sleep time. And I was tweaking with this value, and you could play with it a little bit, because this is the time that we're allowing for new measurements to come in, and it's charging up the piezo, and that peak detect circuit is charging up. So, if that's too short, you might miss the vibration altogether. So you want it to be long enough, but you don't want it too long, because if it's too long, it's just going to charge up and it's going to be too sensitive. So anyway, that's another value there to play with, or maybe even kind of go through a loop, like take 10 measurements, take 20 measurements at a time, average them out, so anyway, just that value seemed to work pretty good for me and my dryer here, so that's what I went with. And then right after that, it wakes up and grabs the two analog readings, so grabs the piezo reading and the light reading, and then kills power immediately to the op amp and voltage divider. So it drives that pin low and kills power to the devices. Here's a little bit of debugging, which is commented out. And I wanted to comment this out because this is just wasted time for the processor to be on for. I want it to be on for as little time as possible. So get in, do its job, go back to sleep. Okay, but what that would do is just print out the raw values. So the first thing it does, though, after it takes the measurement, is check to see if the button was pressed. So this flag is set true if the button is pressed down here, sets that flag to true. And jumping back up here, that would be true. And of course, if the button is pressed, we want it to turn off the alarms, and that's exactly what it does. So first it clears the flags and then sets the alarm flags here to false. So it turns off the alarms. So now we get into how it determines whether or not it should be alarming, or the states, like is the lamp on and off for the light, is it vibrating or not vibrating for the dryer, and that's what's handled right here. So the first part is for the light sensor, and you can see here we've got like this counting system, which kind of helps with just filtering things out. I don't want it to just take one reading and think, oh, that's it. The dryer must be done. I want it to actually count up to kind of filter it out. Make sure that the dryer is on or off. Make sure that the washer is on or off. So that's what it does here. So if the light is on, count up. With this alarm count. If the light is off, count down. So if the washer if the alarm gets all the way, this counter gets all the way up to 10, we know that the washer is done. The lamp is on. The threshold has been there above the threshold for 10 times in a row. So the lamp must be on and the washer must be done. So we fix that at 10. If the count gets down to 0 and pins at 0 here, then we know that the lamp is off. Okay, so if down here, I'm going to skip this part right here and go right here. So if it was pinned at 0, then we know that the lamp is off. So turn off the alarm and arm the system. So now the light is armed. And then it will count up from 0, because when the lamp turns on, it will start counting up from 0 and eventually get pinned at 10. And since we armed it already, the alarm will trigger. So now it's like, okay, we were off, now we're back on. Turn on the alarm and then kill the armed, because now I want it to wait for the lamp to turn back off before it arms itself again. So that's kind of how that works. And then down here is where we handle the piezo alarm. So it's the same kind of thing. Counts up when the dryer is off. So it's a little bit backwards, because we are actually trying to trigger the alarm state when the dryer is not detecting the vibration, right? Because it was vibrating, and that's how we know it's on. It was on, and then when there is no longer vibration, we need to detect that and then alarm. So that's what's going on right here. So it's counting up when the dryer is off, counting down when the dryer is on, okay? So it'll pin itself at 10 when the dryer is off, and then it'll pin itself down to 0 when the dryer is on. So if you kind of think through this and walk through it, maybe it'll make a little bit more sense. I don't know. This is kind of a confusing way to go about this. But again, we'll just consider right now the state where the dryer's just sitting there idle, okay? So it'll pin itself at 10, and it'll just sit there at 10 all day long, but it's never armed. So right here, it'll just sit there, and it's never armed because it was never on. But as soon as you turn the dryer on, this value will count down to 0 and pin itself at 0 and arm itself, goes to true. Now it's armed. And then when it counts back up to 10 because the dryer is now off, it will throw the alarm and turn on. So I hope that kind of makes sense. And then right here is where if either one of those states is alarming, turn the buzzer on. Otherwise, turn the buzzer off. And that's pretty much the whole code there. And then go to sleep with a prescaler of 33 for an 8-second sleep mode. So it'll enable the watchdog to sleep at its maximum sleep time, which is 8 seconds. And of course, you could loop this to get longer sleep times. And I measured a sleep current of like around 6 microamps. So that's going to give me years and years of battery life off of the 9-volt battery that I've got hooked up there. So anyway, that is pretty much the whole code. Hopefully that makes sense. Kind of a cool, fun project. And actually serves a purpose here. And hopefully I won't have wrinkled clothes anymore. So hope that was interesting to you. Thanks for watching.